Okay, so in this video we're going to do two topics, CC3, atomic structure, and CC4, the periodic table. Atomic structure is relatively straightforward. Okay, I've drawn a model here of an atom. The center of the atom is called the nucleus, and in the nucleus you have got positive protons and you have got neutral, which means no charge, neutrons. So protons and neutrons in the nucleus, protons with a positive charge, neutrons with no charge at all. And then surrounding the nucleus you've got shells, and in those shells you're going to find the electrons. Electrons have a negative charge. So we have a look at this table over here. I've got my three subatomic particles. I've got their charges, and you also need to know the mass, how heavy they are. So protons and neutrons both have a mass of 1. Electrons are lighter, okay, but you can't say they have 0 mass. You have to say they've got 1 divided by 1835, and that means they're 1835 times lighter than a proton and then a neutron. Okay, I want you to press pause and I want you to do the question on the following page. Just question 1, fill in that table. Okay, because the first one has a +1 charge, I know it's a proton. Because the second one is located in the shell, I know it's an electron. And then I just need to fill in everything else, alright? So for charge, +1 for proton, -1 for electron, 0 for neutron. You do need the plus and minuses, and you need the ones. You could also write here no charge or neutral, and you get the mark. Mass for proton is 1, for neutron is 1, and for electron it's 1 divided by 1835. If you write that as a decimal, it's 0.0005, or you can write the word negligible. Location, protons are found in the nucleus, neutrons are found in the nucleus, it's just the electrons that are found in the shells. Okay, so the first person to propose a model for atomic structure was a guy named Dalton, and this is what he thought. He thought atoms were the smallest particle, that they couldn't be broken down into anything smaller, and he thought that every atom for an element was identical, all right? We now know that that's not true, okay? So you need to know what Dalton thought, and you need to know what we think today. So Dalton thought atoms couldn't be broken down into smaller. Now we know that they can be broken down, and they can be broken down into protons, neutrons, and electrons. So protons, neutrons, and electrons. He thought that all atoms of an element are identical. So if you had sodium, that every sodium atom was identical, or carbon, every carbon atom is identical. We now know, and we'll look at this in a minute, that isotopes exist. Okay, and we'll look at isotopes in a second. He thought that every atom for an element was identical. We now know that isotopes exist. All right, I want you to do question number 2 on the next page. Alright, so there's your answer. We can break atoms down into subatomic particles, which are these guys here, and we now know that isotopes exist. Alright, next little thing we have to do. If you look at any element on your periodic table, you'll see that there are 2 numbers next to them. Okay, there's always a bigger number and a smaller number. This bigger number is called the mass number, and the smaller number is called the atomic number. Just remember that atoms are small, so the smaller number is the atomic number. The atomic number tells you the number of protons. Okay, so it tells you the number of protons that the atom has. The mass number, okay, if we come back up here, there are 2 particles that have mass. Protons have mass and neutrons have mass. The electrons are so light we don't really count them, but protons and neutrons have mass. So the mass number, this is the number of the protons and the number of the neutrons. They're both of them combined together. So the number of protons and the number of the neutrons. And using these 2 numbers, we can work out the protons, electrons, and neutrons in an atom. So the number of protons is the small number, that's 11. The number of electrons is always the same as the number of protons, so that's going to be 11 too. And then the number of neutrons is the big number minus the small number, and I get 12. So it's always small number, big number minus small number, if you write it out as P, E, and N. So just make sure you've got it in the same order as I do if you're going to do small, big minus small. Right, have a go at numbers 3 and 4. All right, so atomic number is the small number, okay? You can't learn that it's the number at the bottom. It's just the smaller of the two numbers. 3 is smaller than 7, so atomic number is 3. Mass number then is the bigger number, which is going to be 7. For this, I do small, small, big minus small. So protons is small, that's 3. Electrons, small number, that's 3. Neutrons, big number, 7, minus small number, 3. And I end up with an answer of 4. So if we look at the overall charge on an atom, okay, you'll see that the two particles have charge. Protons have positive charges and electrons have negative charges. So if I look at my example here for sodium, I've got 11 protons, and that means I've got 11 positive charges. I've got 11 electrons, that means I've got 11 negative charges. And I've got 12 neutrons, but neutrons have got no charge at all. So I've got 11 plus, 11 minus. Overall, I have got a charge of 0. 11 minus 11 is 0. So the overall charge on an atom is 0 because the number of protons and the number of electrons cancel out. So if you're asked, okay, you will be in a second in my questions, why atoms are neutral, you'll say they have the same number of positive protons and negative electrons. So same number of positive protons and negative electrons, so the charges are going to cancel. Right, have a go at writing that down. Do question number 5. Alright, so to phrase this, you're going to say that there's the same number. You have to say same number of positive protons and negative electrons. If you just said the protons and electrons cancel out, you don't get the mark. You have to say same number of positive protons and negative electrons. Alright, last thing we need to look at in CC3, isotopes. Alright, so I've drawn out 3 different examples here. I've said they're all lithium and they've all got an atomic number of 3, but the mass number is different every time. I've got the number 6, 7 and 8. So let's have a look at how this affects our protons, electrons and neutrons. So we said it's always small, small, big minus small. So that's going to be 3, 3, 6 minus 3 is 3. Small, small, big minus small. Small, small, big minus small. Okay, so when I work it out, I'll see that there's some things that are the same. I'll see that the number of protons is 3 every single time. I'll see the number of electrons is 3 every single time. But I'll see the number of neutrons has gone from 3 to 4 to 5. And these are called isotopes. And your definition of an isotope, they're atoms with the same number of protons. You don't need to mention electrons at all, okay? So you say atoms with the same number of protons but different number of neutrons. So that's what isotopes are. Same number of protons but with a different number of neutrons. And they just occur naturally, okay? So lithium will just exist in 3 different forms. Because it's got 3 protons, that's how we say it's lithium. If it didn't have 3 protons, it just wouldn't be lithium. But because it's got 3 protons, we say it's definitely lithium, okay? All that's changing is the number of neutrons, all right? So if I'm looking at these guys all have different mass. One of them has a mass of 6, one has a mass of 7, and one has a mass of 8. But other than the fact that they have a different mass, they all act in the same way. Because it's the electrons that are involved in chemical reactions, they will carry out the same chemical reactions. It's just their mass that's going to be different. Alright, last question then for CC3. What is an isotope? See if you can give me that definition without looking back. Okay, so there it is, an atom with the same number of protons but a different number of neutrons. Alright, so CC4 is about the periodic table, and one of the things you need to know is just how the elements are arranged. So you've obviously got lots of different elements here. If we look at how they're ordered, it's not alphabetical order. It's not that we start with all of the A's and move on to the B's. It's to do with the numbers, and there's 2 numbers, the atomic number and the mass number. And if you look, you'll see they're arranged according to atomic number. So there's a small number at the bottom. It goes from 1 to 2 to 3 to 4 to 5 to 6 to 7 and so on and so on and so on. So you're using the atomic number and you're ordering them from smallest to largest. Now originally the guy who made the first periodic table was a guy called Mendeleev, and he didn't use the atomic number, he used the mass number. So he used the mass number, but now we use the atomic number, and that's an important difference that you need to know. Okay, so if we're looking at the periodic table, Mendeleev, the guy who came up with the first one, arranged the elements in order of increasing atomic mass, Now we use increasing atomic number. The other thing you need to know about how they're arranged is you'll see not all of the elements go across in one really big long line. After 8 elements, he started a new row, then after another 8, he started a new row. So why do they do that? And in both cases, whether it was Mendeleev or the modern, you've got elements with similar properties. So in terms of how they react and what they look like and all the rest of it, elements with similar properties are in the same group. And you can write that for the Mendeleev and the modern. So all of these elements here, lithium, sodium, potassium, they've got stuff in common, so they're in the same group. These elements here, oxygen, sulfur, selenium, they've got something in common, so they're in the same group. That's the other thing we need to know, is that in the periodic table, when you're going down, that's called a group, and when we're talking about those rows going across, that is what we call a period. All right. Actually, I'll tell you a few more things. Other differences between Mendeleev and modern. Mendeleev, because it was so long ago that he proposed his periodic table, not all of the elements had been discovered, so he had some gaps in his periodic table. Just because they hadn't all been discovered, but he knew that there was likely more, and he just left gaps. The other thing to note is that there was no group 0 elements in Mendeleev's table. So if we look at the periodic table today, in group 0 I've got helium, neon, argon, krypton. These elements are called the noble gases, and Mendeleev did not include any of them in his periodic table. And the reason why is they hadn't been discovered. And they hadn't been discovered, if you remember, these guys are really unreactive. We say they're inert. And because they're unreactive, they were harder to detect. So back in Mendeleev's day, none of these elements had been discovered, so all of group 0 is missing from his original periodic table. Right, now I want you to have a go. I want you to do 7, 8, 9 and 10. 7, 8, 9 and 10. Alright, so how are elements arranged in the modern? That's according to increasing atomic number. You need the word increasing. Mendeleev used increasing atomic mass, but in both cases you can say elements with similar properties are in the same group. Why did he leave gaps? Some elements hadn't been discovered, so he left gaps knowing that they would later be found, and he wanted to be able to put them in. Completely left out group 0. The reason why, they're so unreactive that they hadn't been discovered, so he didn't know that they exist, and they were just left out completely. Alright, last little thing is electron configuration, and that just means how are electrons arranged. So I've drawn out these shells. The first shell is the shell on the inside, closest to the nucleus. You can put a maximum of 2 electrons in the first shell. The second shell can hold a maximum of 8. The third shell can hold a maximum of 8. And any electrons that you've got left over will go into that fourth shell. So if I write the electron configuration for sulfur, okay, using the atomic number, I can see that sulfur must have 16 electrons in total. I can put 2 in the first shell. I can put 8 in the second shell. That means I've put in 10 electrons in total. I've got 16, so I've got 6 electrons left, so I end up with 286. So just double check that these 3 numbers add up to the atomic number, and that's the electron configuration for sulfur. 2 in the first, 8 in the second shell, 6 in the third. If I do another one, calcium has the numbers 14 and 20 next to it. The number of electrons is a smaller number, so I'm using the number 20. I can put 2 electrons in the first shell, 8 in the second shell, that's 10. Another 8 in the third shell, that's 18. And then I've got 2 left over for the fourth shell. So if I add these up, I get to 20, and these are how the electrons are arranged. This is called electron configuration. Once you've got your electron configuration, you can use that to work out what group and what period an element is in. So if I want to work out the group, I always look at the last number. Sulfur is in group 6 because it's got 6 electrons in the outside shell. Calcium is in group 2 because it's got 2 electrons in the outside shell. Alright, so you're just looking at the one on the outside to see what group it is in. The other thing you can do is you can work out what period an element is in, and for this you are just counting up the electron shells. So I needed 1, 2, 3 shells. That means it must be in period 3. For the next one, calcium, I needed 1, 2, 3, 4 shells. That means it must be in period 4. So the last number, the number in the outer shell, tells you the group, but the number of shells you needed, that tells you the period. All right, have a go at doing 11 down to 14. All right, 19 electrons, 2 in the first, then 8, and then 1. Add them all up and you get 19. I can tell it's in group 1 because there's 1 electron in the outer shell. You can't write the last number is 1. You have to say what the last number represents, which is the number of electrons in the outer shell. How can you tell that it's in period 4? It's got 4 electron shells. Again, you can't write it's got 4 numbers. What do those numbers mean? It means there's 4 electron shells. Sulfur is 286. What group? I look at the last number. It must be in group 6. What period? I count how many numbers. It must be in period 3. Right, that's all of atomic structure and periodic table.